All right, good morning, everyone. So we'll start today by finishing what we ended in the last lecture, namely having a look at frictional forces and how these may be included in the Lagrangian formalism. So in the previous lecture, we derived these Lagrange equations. Which quite generally have this form. This L here contains the kinetic energy and the potential energy, whereas this Qi, when written like this, is a generalized force which cannot be derived from any potential in the system. So we saw that if the system is conservative, so that all the forces may be derived from some potential, then this is just zero. So when we write the Lagrange equation like this, it's implicitly assumed that this Qi contains only the forces that cannot be derived from potentials, such as friction. And I tried to argue in the previous lecture that the way you can model friction typically in a system is to include a term in the equation of motion which is proportional to the velocity of the system, because this will introduce a damping term in the solution for the system. For instance, if you add if we have this equation of motion, just a spring, for instance, oscillating with a constant k. This is Newton's second law. This is the spring force. It's typically something like the solution for x typically looks something like this. And then for the actual solution, you take the real part to get rid of the I, etc. This is the general solution. Now, to model friction or resistance of some sort, we could add a velocity-dependent term with a constant lambda here that provides the magnitude of the frictional force. And what happens then is that the solution takes some kind of form like this. So you get an extra term here, which is a damping term. You see, as t becomes large, it takes the amplitude to 0. And so we, motivated by this sort of ansatz, we introduced in the Lagrangian formalism the so-called Rayleigh dissipation function. Can you see when I write here in the back? Yep. Which in 3 dimensions would look like this. So it's basically just a generalization of this velocity-dependent term. Because with this function, the frictional force would be related to this Rayleigh dissipation function, curly F. Like this. So this nabla v means gradient with respect to velocity. So conventional gradient, you have derivational operators with respect to x, y, z. Whereas this gradient would then be with respect to vx, vy, and vz, respectively. Okay, so if we accept this sort of model for how to include friction, we can make some statements about, for instance, the work that is done by friction in the system. So if we consider the infinitesimal work dWf as the work done by the system due to friction, this is a definition of work. Force dotted with the displacement vector. I can rewrite dr as the velocity multiplied with dt. And by then using this Rayleigh dissipation function and this relation here, we get this. So I just omitted the sum over I here. So we're just considering one particle, for instance, for simplicity. And this is just two times the dissipation function and dt. So you can see that the rate of energy loss, the rate of work done by the system due to friction is just 2 times this dissipation function. So it's a quite simple expression. Okay, so let's now see how this fits into Lagrange's equation when we have this generalized force Qi. So in order to say something about that, we would have to go back to the original definition of the generalized force. And if you look back in your notes, I think we did it 1 or 2 lectures ago. You would find this. As the definition for the generalized force. Okay, well, we have an expression for F here, so let's try to use that. So what I did here was to use a property that this term here is equal to this term. So I just added the dots here and here. And this is a property which we also introduced a few lectures ago. And it's defined or proved in the compendium, as far as I remember. Okay, and now we're actually in a position to make a further simplification, because we have a derivative with respect to v here. This is a gradient with respect to velocity. And here we also have velocity, because it's a time derivative of r. So this means that the generalized force for friction is this. And just to show you that this is similar actually to a conservative system, keep in mind that in that case, we have this expression for the generalized force. It's just a gradient of, or the derivative of some potential u, or v, or whatever you want to call it, with respect to the generalized coordinate q, small qj. So it's the same thing in principle. You have the generating function here, f, curly f, and then you have with respect to velocity instead of position. So if we insert this result into Lagrange's equation, we get this. So this equation tells you how Lagrange's equation is modified in order to include frictional forces, which may not be derived from some potential. So we get this extra term here. So this can be good to keep in mind if you're ever faced with the task of modeling some system with friction. Very well. So we've introduced the Lagrange formalism, and I figured we could take a look at a couple of examples to sort of show you how you can do, how you can analyze various systems in practice. So, examples. And let's start off pretty easy. We consider one particle and Cartesian coordinates, and we consider a particle which is moving in zero potential. So it's a particle with purely kinetic energy. Okay. Could anyone help me out? What is the Lagrange function for this system?
Just t?
Yes, just t. So in Cartesian coordinates, this would be written like this. Okay, so let's set up the Lagrange equation. We have this equation for the x coordinate. Remember that Lagrange's equation is in fact several equations. You have one equation for each generalized coordinate. So for the x coordinate, you have this. All right, t is independent on x. So this term is 0. So what we get is Newton's second law for a particle moving without any force acting on it. Mass multiplied with acceleration is 0. Okay, let's step up the difficulty a little bit and move on to polar coordinates. So then we have the following. So whereas the generalized coordinates in this case were x, y, z for a particle moving in 3 dimensions, in polar representation, the generalized coordinates are r and theta. So we're considering now movement only in a plane, 2D plane. Again, we consider the situation where the particle is not subject to any potential. So the kinetic energy looks like this. So we would now have to find an expression for x dot and y dot in terms of these polar coordinates. Well, we can just use these transformation rules. So we get this. First derived with respect to time on r, and then cosine theta. Same thing for y. And we insert this into our expression for the kinetic energy. And find this. So we see that the kinetic energy actually consists of 2 parts. It consists of the velocity in the radial direction, and also the velocity associated with any angular motion due to this theta dot term. And we could actually see this, sorry, straightforwardly from the geometry of the system. So if the particle is here to begin with, and then moves here, and these 2 points are distinct by both a possible change in r, so we have delta r here, and there's also an angular displacement delta theta. So we would have to consider the limit of delta theta and delta t goes to 0 to find the instantaneous angular velocity. So we'll get this and just square these 2 terms, and you'll find them here. Okay, so we have the Lagrangian for the system, which is just the kinetic energy. So let's try to set up the Lagrange equations. And to make the system slightly more general, let's in fact include these, the generalized force in the system. So we take into account the possibility that we might have some force acting on the particles. Now, in a 2D plane, you can decompose the force into 2 components. You can have a radial component of the force, which from the definition of the generalized force, this is the definition we used here. So this is just Fr. We can use this notation. And then we have the angular part of the force. Again, we use the definition of the generalized force like this. So keep in mind that r and theta are our generalized coordinates. They are our small q's in the system, the generalized coordinates. So we get this for the generalized force, the radial components of the generalized force and the angular components of the generalized force. So let's now put these into Lagrange's equations. We have 2 generalized coordinates, r and theta, which means that we should have 2 Lagrange equations. So the Lagrange equation for R is then we consider it just term by term. So first we have to check if the kinetic energy contains any components R dot, if it has any dependence on R dot, and it has. So this is mR dot. But in addition, we know that the Lagrange equation contains a derivative of L with respect to Q, or in this case R. So we have to check if L has any dependence on R. And in this case, it actually does, due to this term. So then I can construct the complete equation by taking the time derivative of this first term minus this term, like this, and then setting them both equal to the generalized force for this particular generalized coordinate, R. Right, so that was Lagrange's equation for R. Now we'll consider Lagrange's equation for the second generalized coordinate, theta. So again, we'll consider just term by term to make it very transparent how we get the Lagrange equation. So first we'll consider if the kinetic energy has any dependence on theta dot. And I've erased it now, but if you consider your notes, you will see that it has, due to the second term, due to the angular velocity. So we get this. Then we consider if it has any dependence on theta, which you will find that it does not. So we get this. These two terms are just a time derivative of this term. So if I derive this expression with respect to time, I first get mr squared, multiply with the double time derivative of theta, this term, and then I would also have to derive r with respect to time to get this. And so this should be equal to the generalized force associated with the generalized coordinate theta, which we derived over there to be equal to rf theta. And this gives us a complete description of the system. These two equations, this one and this one, are the two equations of motions that we can use to solve for r and theta, to find r and theta as a function of time, which would describe exactly how the particle moves. If we know r as a function of time and theta as a function of time, we would know exactly how the particle behaves. So to do this, we would have to know the mass of the particle and also the forces, Fr and F theta, if they exist, which act on the particle. Okay, we'll have a look at one more example. This example is meant to illustrate to you how sort of approaches which you may have been accustomed to using previously, such as balancing forces. This is probably a method you used a lot in high school to solve mechanical problems. You set up sort of a force balance in each direction, and then you solve for each of the forces. This is supposed to illustrate that there is an alternative way, an alternative approach to solving for such systems. So let me draw it here. So we have some device here where we have two masses attached to a string, and the total length of the string is L. So the distance here is x, and this distance is L minus x. Now, how many independent or generalized coordinates would you say we need to describe this problem? If these masses just move up and down. 1. I agree, just 1. Just the x coordinate. And the reason we only need 1 is that we have constraints in the system, right? They're attached to this device here, so they can only move up and down. So the constraints are taken into account in this way. Okay, so say we're faced with the task of finding x. How does x depend on time for this system? Say we're charged with the task of finding an equation of motion for x that you could use to determine x. One way to do so would be to use this force balance, as I mentioned. You could use, for instance, that you have some gravitational force acting on M1, but you also have a force acting on M1 from this strain, from this rope here. And similarly, you have some balance here. And you could use these equations to find a net equation for how x develops. But let me show you a different method. If you want to use the Lagrange formalism here, we have to find L first. That's the first thing. So it means we have to find T and V. Well, this dotted line here it represents just the reference level of the potential. So remember, I'm free to choose this wherever I like. We can always redefine the reference level for the potential in a conservative system. So if this is 0, then the potential energy has to have this form. It will be negative, because these are lower than this line. Okay. Well, the kinetic energy will be given like this. It's just the 1/2 m velocity squared for each system. And even if you have a minus sign here, it vanishes when you square the velocity. Okay, so this is the complete Lagrangian of the system. Kinetic part minus the potential energy. Okay, what would you do next? You have the Lagrangian, and then?
Start deriving with respect to x and x dot.
Yes. You start deriving with respect to x and x dot. So we have dl dx, for instance, first. Should be equal to this. So let me just write this step explicitly here. First step, find L. Second step, derive with respect to x and x dot to get these results for our particular Lagrangian. And then with this in hand, we can just set up the Lagrange equation. And this is the result. we now have an equation of motion for x and its time dependence. This determines how x would evolve with time. Now we could have obtained exactly the same result by using this other method, by balancing forces, for instance. But imagine now that we had additional masses in the system. We had, for instance, included a mass here, 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 or made the system more complicated in some way. That would give you a real headache in terms of trying to balance forces. But with the Lagrangian method, you would just have to write down the kinetic energy and the potential energy, make these two derivations, and get the result. Much more elegant, much more simple. So whereas there's not a big difference in terms of workload for the Lagrangian method and the force balancing system for such a simple system, the payoff is much larger when things start to become more complicated, when you have more particles, for instance, or more advanced geometries. Okay, we have 2 minutes left, so with those 2 minutes, I would like to try to assemble a reference group in this course. So just a few words about reference group. The one thing which you may be most concerned about is how much work it is. And I can assure you it's very, very little work, almost nothing. The reference group basically meets with me twice in the semester. You first have some 10 minutes meeting with the class just to get some feedback, what's working in the course, what has to change, etc. Then you meet up with me, give me the feedback, and I'll make some adjustments. And then we meet, that's the first meeting, and then we meet towards the end of the semester just to assess, did this work? Did you make any changes? Yeah. Being in a reference group is very little work. It's something you can put on your CV. And most importantly, I think it's a service to your fellow classmates to improve the quality of this course. So the minimum amount of people in the reference group is 2, and preferably I would like 1 man and a woman. The choice of women here is somewhat limited, so no pressure. Do I have any volunteers? Excellent. Okay, perfect. So if you could just come here and I could get your emails, that would be great. So we'll take a 15-minute break.